Okay, hi guys, so in this video we will be seeing the differential form or the derivation for the first order reactions. So let's get started. So for first order reactions, suppose we have a first order reaction which is simply A gaseous converting into B gaseous plus C gaseous. So let's suppose the initial concentration of A was small a, and for B and C it was 0, and let's say we have concentration at time t, and this is, let's say, A minus x, x and x. So rate of reaction would be minus dA minus x upon dt, which is rate of disappearance of A, which has to be divided by the stoichiometric coefficient of A, which is 1, which would be equal to rate of appearance of B, which would be dx upon dt. Stoichiometric coefficient is 1. Similarly, rate of appearance of C, which would be equals to rate constant times concentration of concentration of A at this particular point of time raised to the power 1, because it's a first order reaction. So we can see from here that if we open up this differential form, it would be dx by dt, which would be equal to k into A minus x. So this implies dx upon A minus x would be equals to k dt. Now we integrate this differential form, so we will be getting minus ln A minus x would be equals to kt. So from this we can write that obviously kt plus c. So now when t equals to 0, we know that x was 0, so c would be equals to minus ln A. Just substitute the values of t and x in the equation to get the value of c. It would be minus ln A. Okay, so finally we got the equation like ln A minus x would be equals to kt minus ln A. Okay, so from this we can write k as ln A upon A minus x divided by 1 by t. And as we know that this rate constant would also be equal to rate of disappearance constant, or rate of disappearance constant, or rate constant for disappearance, any term you can use for it. Why? Because we can see that dx by dt would also be equals to pardon me, this can also be written as kd times A minus x, because this is the rate of disappearance, and fortunately the stoichiometric coefficient is also 1, hence this kd A minus x would be equals to k into A minus x, so kd would be equals to k. Okay, so we can also write that k or kd would be equals to 2.303 upon t. I'm just converting it into log from ln A upon A minus x. So this is the form which we get, or the equation of rate constant for a first order reaction. Now we know that concentration of reactant after time c after time t rather is a minus x. So just substituting the value of x from this equation. So if we substitute the value of x from this equation, what we would be getting? So simply we have, from this we can write kt equals to ln a upon a minus x. So doing some mathematical calculation here, that minus kt would be equals to ln a minus x upon a, taking the exponential power here. So e to the power minus kt would be equals to a minus x upon a. So x would be equals to a minus a to the power minus a minus e to the power minus kt. So this would be first a e to the power minus kt, which should be equal to a minus x. From this, x would be equals to a minus a e to the power minus kt. So this would be the value of x. So just substituting this value here, so we would be getting a after time t would be equals to a minus x. Value of x is a minus a e to the power minus kt. So this would be a e to the power minus kt, and a was the initial concentration, so we can write that concentration of a at any point of time would be a naught e to the power minus kt. So theoretically, after infinite time, we can say that the concentration of A is 0, or the time completion is infinite. Theoretically. And why I am saying this, because when you put t equals to infinity, then a to the power minus infinity will become 0, and then at will become 0. So the time at which the concentration of the reactant becomes 0 is the t completion. So theoretically, after infinite time, or rather infinite time is required, infinite time, we can see completion of reaction. Okay, so let's now move to another topic, which is degree of dissociation. So degree of dissociation would be alpha equals to x upon a which is nothing but the amount of reactant which has dissociated into products divided by the initial amount of reactant that was present in the mixture, or not in the mixture, initially amount of reactant which was present before the reaction proceeded or before the dissociation of A started. So by amount we mean here concentration, because x and a we are talking in terms of x is concentration of products at any point of time t which has been dissociated from A, and A was the initial concentration. So we are talking about concentration here. So alpha would be equals to, for first order reaction, 1 minus e to the power minus kt. Why? Because we already saw that x is equals to a minus a e to the power minus kt. Hence x by a for first order reaction would be 1 minus e to the power minus kt. Okay, and similarly percentage alpha we can easily calculate by 1 minus e to the power minus kt multiplied with 100. And we have also seen for a first order reaction that K is equals to 1 by T ln A upon A minus X. So from this we can write that T equals to 1 by K ln, divide the numerator and denominator with A. So we would be getting T equals to 1 upon K ln 1 upon 1 minus X by A, which would be alpha. Okay, so this we can also write as KD, because the rate constant and dissociation constant is same, as the stoichiometric coefficient of A was 1. So this is an important formula, so please remember this. So with this we come to the end of this lecture. In the next lecture we'll be talking on the half-life for the same, and we will also be seeing some graph, and we'll also see the independence of initial concentration of how the independence of the initial concentration of reactant has an effect on the course of the reaction or on the rate of reaction. So till then, good luck and goodbye.